Hello, this is Dr. Pat. We're talking about finding that normal vector to a surface. Some things happened in class, and there's some questions. I just need to clarify them. And so the big question is, do I use for the z component of that normal vector, do I use a -1? Or do I use this partial of f with respect to z? So which one do I use? And so some people have the question of like, where'd this big F even come from? I thought we were using small f's. So let's take a look at some things. So which one do we use? That's what we're looking at here. Which one do we use? The one here on the left with the small f's and the -1, or ooh, this nice one here with the capital F's? Are the f's different? That kind of stuff. So let's take a look at that and do some quick exploring and find out what's going on. Okay, so now I want to make a connection back to Calc 1 there. And when we're looking at derivatives, we did derivatives kind of in two ways, you may recall. Explicit and implicit were some terms that you may have heard before. And explicit basically is our way of saying you can solve for that one variable. So in this case, back in Calc, we were able to solve for y. We can make the statement y equals. So that's what we call an explicit, the explicit statement of y equals. But on this other one here on the right, the implicit one is please notice that we've got a y inside of an exponential, we've got a y squared, and algebraically we're not going to be able to solve for that. So if we're going to define the derivative dy dx, we would have to do it implicitly. Okay, so we'd have to kind of work around the system a little bit and do some algebra to solve for that. Okay, so that's kind of what we did before. I just want to bring that to your attention that one method we used was when we were able to solve for the variable and when we could not. So that's going to be key for what we're going to be looking at, is whether we use the -1 or the capital F there. Okay, so now in multivariable calculus, there are times when we can solve for z and we can get a nice little formula. We can make the statement z equals, and just like in Calc 1, we do have some relationships where we are unable to solve for z. So how do we do this? How do we go about this? Well, when we're able to solve for z, we have we basically have been calling these the expression here on the right hand side, the small letter f, and so we've been saying that this is a multivariable function for f, small f, with the inputs of x and y. And so that's kind of what we've been working with. So now when we can't solve for z, and we have to do this implicitly in the roundaway, we're going to call that whole right side over there, we're going to call that capital F, and it's going to be a multivariable function of x, y, and z. We don't need c is a number. It could be anything. It could be any number. It could be 0. It could be whatever. We're going to keep it on the left hand side because we're going to be doing derivatives, and just remember the derivative of a number is 0, so it goes away anyways. So that's not going to be the main focus. And so that's kind of what we're looking at here. So when do I use these two vectors for my normal, for my surface? Well, if you can solve for z, then go ahead and use the the partial of x, partial of y, and then -1 automatically works for you. If you can't solve for z, then do it implicitly in that approach, and you can just basically bring everything to one side except for the number. If you really wanted to, you could bring over the number, because when we find the normal, the x, y, and z components of that normal, we're just doing the partials. That's what it is, the partials of everything, even with the z's there. So that's kind of when you use one versus the other. Okay. Now, where does this come from? So what's the background? What's the development of this? Just kind of want to look at some things and the extension of level curves. Remember, level curves, those have the same z value. So on your surface, each point on these little lines right here have the same z value. In this case, a z value of 4, a z value of 5. We call them different. You can call them whatever numbers you want. They're constants. So they have a constant. So the graph has a constant value right there. Okay, and so then when you squish all that down, you move those nice level curves and you just draw them in the XY plane. You get these nice contour maps kind of things going on here. It's kind of like those squishy cups, if you ever had those squishy cups as a kid or you're going camping. They're just basically taking the edges and they squish down, and then they make these kind of nice little curves this way. Now, what I want to talk about is level curves and the this is an example. This little vector right here coming off this curve right here, this level curve when k is 5. Basically, if you call this function up here on the left hand, you call that f of x, xy, excuse me, then this vector right here that I'm looking at here is the gradient. It's the partial of f and comma the partial of y. And so that's kind of what we're looking at. This vector right here can be described or can be made quickly by just doing the partials. Okay, now, one of the key points that we found out in a previous section was that gradient, of course, this is called the gradient when you do the partials like this, put it in vector form. That's called the gradient, and that's orthogonal. It's perpendicular to that level curve. So at that point, that gradient right there is going to be a nice little right angle. It's going to be perpendicular, and so that's really kind of cool. That's orthogonal, because orthogonal is good for normals, right? Because that's what the normal is. A normal vector is orthogonal to your surface or to another line that you're playing with, depending on what dimension you're playing with. Okay, so that's what we're looking at. We're looking at the gradient is orthogonal to the level curve. Now, let's take a look and see how it looks like on the original surface. So it's orthogonal to the level curve. So let's take that vector and we put it up here, extending off that same point kind of thing here on the y-axis, that point right above 5 right here at the on the y-axis. That's coming out, that vector. Because this vector was originally made in the xy plane using the gradients and two components there, this thing right here is parallel to the xy plane. And that is not orthogonal to the surface, because the surface has a little bit of an angle to it. It's not orthogonal because we do have the two partials there, but then because it's parallel to the xy plane, our z component is 0 for this vector, and so it is not orthogonal to the surface. Because orthogonal to the surface, we need a vector that's kind of angling out from it to make that 90 degrees. This blue line is orthogonal to the level curve here. That's the key thing, level curve, but not necessarily to the surface in that way. So that's the thing. Remember, you get a lot of vectors can be perpendicular to a level curve in 3D, because you can kind of like spin all the way around that level curve there, and you can make all kinds of normal vectors, you know, just rotating around. And so that's the catch there. You got you got an infinite number of orthogonal vectors. But so this one is orthogonal to the curve there, that line. However, it's not to the surface. And so we need that green one here, and it happened to be the negative one that did it for us. Okay, so now let's go find out some more things about this and find out how can we get that capital F X, capital F Y, capital F Z if I had to use -1 again. So let me take a look at here. So before I really get into it, I just wanted to make sure not to blow people's minds, but a layer of 4D, 4 dimensions, is a 3-dimensional object. So if you kind of like an onion in a way, or just kind of like that layer idea. So what we're doing is we'll be playing, if you're playing with 4D, then a 3D object is a layer of it. Just like in the previous slide here, a layer, kind of like a layer here on the surface here, is a 2-dimensional object here from the 3D. So we started with the 3D surface, one layer here, the level curve, because this is, you can imagine this surface is actually just an infinite number of those level curves, kind of like cloth and a strand of stitching and things like that. One strand of thread would be like a level curve, and that's what you're looking at. So 2D level curve makes up a 3D object, surface object, so that we're going to do the same thing here. So a bunch of 3D objects make up the 4D object. Okay, so keep that in mind. All right, so I'm starting off and just having this graph here of this this relationship right here. It's got a z-squared, so that we got a problem there, because do you want the plus or minus part of it? So that's why it's not necessarily a nice function for us. So I had to graph both the positive version and the negative version to get this graph. Okay, now I want to play with this, and I'm just going to do something right here. Just doing a basic algebra. Didn't do it. Hopefully you see I didn't do any tricks right here. I just brought the z-squared over to the other side, and I looked at it as a negative z-squared. But then I thought, you know what? Let's go up a level. Let's go up a dimension. And so what if we play in 4D? So then we would say, hey, this is the function w equals. And so we can kind of play with that. And so then what would make this 0 equals would make this a level surface, not a level curve anymore, because we're in 4D. I know I can't show you the graph on that 4D, but we're in 4D, and then when we make that equal to 0, when we make w equal to 0, what we actually create is this weird level surface, not a level curve this time, but a level surface, because we're going from 4D to 3D now. We're going down one. So this is basically, think about this, this is a level surface for, you know, some kind of 4D thing out there, and so that's what we're looking at. We're looking at a level surface. Okay, now when we start talking about gradients to the levels, basically we found out that the normal, that the gradients of each thing is the normal to the level. So the gradient on a 3D object is orthogonal to the 2D level curve. So what we got going on here is this 4D object. We go to a level surface. The gradient of this W guy is going to be that. Well, that's what we're going to be finding out. So you call that all of f. Okay, so we got x, y, and z's in there. So we got a function. We'll call it big F this time, not the small f. And so then what we're looking at here is this gradient. That's going to be the gradient to this level surface. And when we do this gradient, wait a minute, this level surface is actually the surface of this relationship. So basically, we just did some twisting and turning around here. So we went to 4D to kind of play around with it so that we could label this thing as a level surface. And that means we can find the gradient of this thing, and that's automatically orthogonal to this level surface. But then wait a minute, this thing was really our original surface that we're playing in 3D. So if something is, orthogonal to the level surface, then it's actually orthogonal to our original surface that we're playing with for this relationship. So that's how we get to play around with that. So it's kind of like if you can't solve for z explicitly, then we can kind of play things around and we can kind of go over here and say, let's make this pretend that this is a level surface. And then we can use its gradient, and then that way that gradient there is working for our level surface, or for our surface that we're playing with. So that's kind of a weird twisting and turning that we're doing. We're just kind of going from 3D to 4D and then back to 3D. Okay, and so now let's finish up that -1. Where did that -1 come from when we were able to solve things explicitly? So I'm bringing this back, but please notice, just by an algebraic, I can bring the z over to the other side, and then what's happening, not only just an algebra step like that, a simple algebra step, move this from just thinking this 3D to 4D. Now we're thinking level curves, and if this is a level curve, then when this is the capital F part of the function, and so if I'm doing my gradient right here, please notice my gradient. When I'm doing this, these two parts did not change. Please notice that we started with the 2x to the third plus 6y, and that's usually called the small f. That did not change when we brought the z over. So when we're doing the gradient of capital F, those first two components are exactly the same as what we originally had with the small f. So that's going to be working fine there as well. And then when we take the derivative of this right here, hey, I got a negative z. The derivative of negative z with respect to z, I'm sorry, I should have said the partial derivative with respect to z, and that's going to be a -1. And so that's where that -1 comes from when we can solve these things explicitly. Okay, so the gradient in that 4D world turns out to be a nice 3D gradient with a -1 there, and so that's really kind of nice for us in that way. Well, yeah, so it's working out okay. So that's kind of where that -1 comes from. The -1, just think of it as a special case of just using the capital F. So that's all we're looking at, just a special case because we're able to solve for z. Hope that helped. Take care and have a good one.